All right, so like I said, when we're looking at these, we can be asked to find a whole variety of them, different aspects of motion. Like in this one, we're trying to find v given acceleration, and now in this case, we're given the velocity, and we want to find an expression for the acceleration. And we know you have two options here. You can either use d dx half v squared or v dv dx. Both of them are fine. Some may be easier than others in given situations. Last time we used half v squared, so why don't we go ahead and try and use v dv dx in this case. So that's just going to be the velocity there, so 3x plus 7 multiplied by the derivative in terms of x, which we are given, which is great. So that would just be 3, which is quite easy in this case, right? So it's just going to be 9x plus 21. So you can see in this case, for part A, using v dv dx is pretty easy. Cool. So now we've got something a bit different. So this time, we have some initial conditions. So we know that it's 1 meter to the right of the origin at, well, initially. So when's that, right? Like t equals to 0. So at t equals to 0, it's 1 meter to the right. So pay attention to the direction in this one. So if it's to the right, it's in the positive direction. But this time, what's different about this, right? We're asked to find the displacement as a function of time. So you're given this stuff in terms of x, in terms of its position, but you can be asked to kind of go between these two ways of expressing our motion. Like we can be asked to go from where it is in terms of its displacement to where it is in terms of time now, which is exactly what we're asked to do. So when you see that, be very careful. Don't just look at this and think, I can integrate easily, because, well, if you do that, then you're going to run into some problems. First of all, because this is in terms of x, and I want it in terms of time, t, right? So just make a mental note of that, right? What we can do, though, is we can start off by thinking with v is equal to 3x plus 7, because that's really all we have to go off. Like, we have our acceleration, but that's kind of further away from what I'm trying to get to. Why this is useful is because if you think about it, right, what can we do with this? How can I just kind of introduce the concept of time here? Well, I know that v, another way of expressing that is, well, that's acceleration, actually. But if I go to, do I have it anywhere here? Well, if you remember just velocity, how do you express that? It's the first derivative here, right? It's our first derivative. And I could rewrite v in terms of that over here. But there's an issue with writing it in this way, because if you look at it, if you're thinking, hey, how can I just go back to my displacement? Well, I could integrate. But the issue with integrating straight up here is, can you think about what that might be? And why can't I integrate straight up with this expression right now? Right, it's because if you look at it, this is saying, okay, I should have x in terms of t, and I've actually got something in terms of x here. So that's the issue, right? This dt is telling you what I'm integrating with respect to, and saying I'm integrating with respect to t, but I have stuff in terms of x, so I can't quite do that. But there's a solution to that. If you remember back to your differential equations, we had a trick. We could separate these dx dt's, we could kind of manipulate it, or we could just simply take the reciprocal. So if I flip both sides, take the reciprocal of both sides, what I end up getting is something like this. I end up getting dt over dx is equal to 1 on 3x plus 7. And now I've fixed that issue. I have stuff in terms of x, which is what I was looking for, right? And I can use an integrating factor here now, right? So I can go ahead and integrate. So t is equal to, now what kind of expression is this? Well, it's a logarithm. So I want the derivative on the denominator on the numerator. So when I need a factor of 3 out here, but then I don't want to change the expression, so I want to multiply that by 1 on 3. And so that's going to be 1 on 3 ln 3x plus 7. And of course, we've got our constant here as well. And we have some initial conditions. So initially, the displacement is 1 meter to the right of the origin. So we have at t is equal to 0, x is equal to 1. So we substitute that in. So 0 is equal to 1 on 3 ln 3 plus 7 plus c. And that means that c is just going to be equal to negative 1 on 3 ln 10. Okay, well, you don't need that as values now because 10 is a positive number already, right? So that's our constant. So let's go back to the original expression now. So t is equal to 1 over 3 ln 3x plus 7 plus our constant, so negative 1 on 3 ln 10. All right. Now from here, Typically we want to have x as the subject, which we don't quite have right now. So what I'm thinking is to put these together, if I've got these logs, I know if I have the subtraction of two logs, I can put them together as one expression. So that's a log law that we have. So I'll factorize out the 1 and 3 first. And now I'm going to be left with ln 3x plus 7 all on 10. And how can I go from here? How can I make x a subject? Well, let's get rid of these fractions here. I don't really like fractions. So 3t is equal to ln of this expression. And then if you remember, ln is just log base e. So what I might do is I can raise both sides by base e. So I get e to the 3t. And then using your log laws, if you put e as the base here, remember your log laws say that basically you end up with the expression inside the log. So I get 3x plus 7 on 10. Now, and I guess we write x as a subject from there. So we just say that's 10 e to the 3t, 3x plus 7. We can rearrange, so I get 3x is equal to 10 e to the 3t minus 7. And so x is equal to 1 and 3 outside of that. Okay? And that's how you can go from, having your velocity in terms of x, doing a bit of rearrangement, integration, and then ending up with x in terms of time, which is what we're usually used to seeing. Okay? So that's, acceleration in terms of x. Well, actually, displacement in terms of time when we originally get back to.